speaking on quantum information technology. Sir, is it audible, sir?
Yeah, I'm able to hear you.
Yeah. It's my great pleasure to introduce our esteemed resource person for today's technical session, Dr. T. Srinivas, sir, who will be speaking on quantum information technology using photonics. And sir has did his PhD from IISC and postdoc from Japan Tokugawa University. And sir has more than 35 years of experience in the field of photonics, integrated circuits, photonic sensors, quantum communication, etc. And sir is currently working as a professor in IISc in the Department of Electronics and Communication. Sir, let me, sir, now I am handovering a session for you, sir.
Yeah, fine. Thank you. Let us get started because you may have less time. I don't know whether you have any more programs after this.
No, sir, only exclusively your program only, sir.
Okay. So I think many of you had already had a lot of quantum because I know about your college. You must have had many talks already. I hope everyone is able to hear.
Is it audible?
Hello. Is it all right? Someone please cross check and verify. We'll get going. Okay. Yeah, let me continue.
Sir, please keep that screen in full mode, sir.
Yeah, I'm just trying to change. Just a minute. Where is that? Hello. Is it all right?
Yeah, sir. No, it's fine, sir.
Yeah, let us get going. So I know your college, there has been some lot of quantum going on. Many of you know already a little bit. So I would like to put a different point of view and from a more basic point of view. Okay. So I would maybe a few comments before we get further down. See, this technology or this terminology, the quantum is very popular now. Many people are interested and lot of scope for the future, lot of applications and
Sir,
so on.
sorry to disturb
Yes.
you, sir. Please go to that presentation mode, sir. Then that screen will be more visible, sir.
Okay. This is full screen. I am seeing full screen here. Is it in the presentation or I don't? Let me just check once again. I will check in my cell phone maybe. See, this is what mode is this? See, this is this the mode that you are talking about?
No
Is
issue,
it
sir.
visible now?
Is it visible? No issue, sir. You can continue, sir. Please.
No, is it full or half or how is that?
No. We are getting full screen only, sir.
Okay. Yeah, let's get started. I was saying that many of you people know about quantum a little bit. And I would like to give some suggestion before going further. See, there's a lot of hype associated with the quantum.
Sir, excuse me, sir. There are 120 plus participants here, sir. 120 plus.
You're able to hear, I suppose, is it not?
Yeah. They're in the seminar only, sir.
Yeah. See, we'll have a lot of interaction. Let us first finish off one round of all the slides. Okay. See, there are a lot of things associated with the quantum. We'll focus on some specific aspects today. Okay. So before going further, I would like to mention that there's a lot of hype associated with the quantum. Many people say quantum and so on. And like AI, you can say compared to AI. As you know, in AI, there are a lot of jobs are there. And whereas in quantum, it's not at many jobs, but most people feel this is the futuristic technology and a lot of applications and a lot of in the future in this. So that is the reason why people are interested. People say that this can solve many problems which we cannot do by conventional means. By classical technology, we cannot solve many problems, like a supercomputing. For example, it can go up to certain teraflops. But people force a new technology, this quantum technology, which can solve many problems in alternative ways. They may not assure that it will solve everything, but what is called quantum supremacy. That means what classical cannot solve, this can solve. Okay, examples are there. As we go along, we'll tell you, like the searching of big data problems, then mathematical computing, like factorizing numbers. These are all can be solved, already proved that quantum technology can solve those. Okay, one more point I would like to mention when you are talking about quantum, there are two broad areas of quantum technology that we come across in the literature. One is quantum devices, like lasers, and so on. So those are devices that will require quantum physics or so, quantum. And then now what we are talking about is quantum information, qubits and all that. These are the two broad areas that people talk about, quantum devices and quantum information. Okay, let us get going. As we go along, I'll tell you a lot of things. So I will focus on the basics first, then we'll go to some applications and how photonics can be useful. As you know, as he has read out my bio, we are interested in photonics, and through photonics, we feel that quantum information technology can be realized. So the question that you usually asked is, why is there no quantum computer until now? In the news, you are seeing that there are many people like IBM and other companies, they are saying, we have built a quantum computer. This is the quantum computer. Pictures also you can see. But if you compare with, see, we would like to compare with VLSI technology. All the electronics has become important and grown and has become practical like this now because of VLSI technology. You can make a lot of electronic components on the chip very easily now on silicon wafer. Of course, a lot of improvements are still going on. Such a technology is not there for quantum. So people feel that photonics will provide such a technology. Presently, people use atomic systems, nuclear systems, and so on to build quantum systems. That's not very convenient or not very suitable for practical applications. They can demonstrate, they can show that they can prove the theory, but it's not so practical. We should keep that in mind. Everyone who is listening to this lecture should go back after this lecture and read a few papers that I can give you also. Some standard papers you should read. Another important point I would like to mention in this connection is you have to learn many things yourself. You cannot learn properly or fully through a lecture like this. Or even sometimes reading a book is also not sufficient. You should think, write your own notes, consider what is this that the speaker is talking about, and so on. So I would suggest self-study is very, very important for this subject. The same thing for many other subjects. So let us get going. This is a brief outline of the presentation. We'll go with a brief introduction. Then we'll see the history of quantum information technology. We'll see what is qubits. Then what are quantum gates. Then we'll see block diagrams of quantum computers, quantum communication link. Then we'll also see what are the futuristic things about technology, in particular photonics, and little bit of work that we have been doing in our lab also I'll put there. I hope that's all right. The organizers can interrupt me anytime. You can call me on the phone if there is any problem with the network or anything. And about 10-15 minutes before, already I have spent 8 minutes, about 10 minutes before we'll close and we'll have a lot of discussion. Discussion is very important. I would suggest, I hope most of you are students from Balnad College and you have very good, he was mentioning that you have a lot of student members and so on. I would suggest, of course, you listen carefully, but don't leave any speaker without asking some good questions. Okay. So let us start with what is meant by quantum. That is a keyword in whole of this lecture. Quantum is a keyword. So quantum refers to refers to states of objects. The states of objects are discretized. They can exist only in certain discrete levels, or so you can say. Like numbers, when you talk about numbers, you say 1, 2, 3, 4, etc. These are all discrete. Whereas when you say real numbers, then it's a continuous domain, something like that. So let us take some other example. Energy of atom is quantized, which means it can have only certain levels, E1, E2, E3, E4. Okay, that we call it as quantized. The energy is quantized. Similarly, many parameters, many properties of the objects are quantized. As an example, I have mentioned about the electron. Electron energy levels are quantized. Then its position, for example, position of an object is not well defined. So is discrete and quantized. Okay. One more example I would like to mention, because we are talking about the photonics. See, photon is defined as a wave. Is it not? Energy. It also has a particle property. That means it has got a certain momentum. It has got a dual nature. And when you go to single photon or basic properties of photon, then you find that the states of the photon are quantized. Suppose I say polarization, horizontal and vertical polarization. They can have only certain discrete values, not all values. For example, they can have 1 degree, 2 degree, 3 degrees, and so on, but not in between. That's what is meant by quantization of the photon state. I have just very odd example I have taken, but similarly, energy. So how do you find all this is an important question. If you have studied quantum physics, you must have come across the Schrodinger's equation. If you are given a potential distribution, you can find out the energy levels. So what you find is actually the solution of the Schrodinger will give you wave function, what is called this wave function. And the square of that gives the probability distribution of the states. I would like to take smaller examples so that you can understand better. Suppose you have a particle at x equal to 0. According to the quantum, you have to describe that by the wave function. So where you can imagine, maybe let me see if there is a slide. I don't think I have a slide describing all the quantum physics, but maybe as we go along, I'll describe that. So there are states of the object. So let us, if you want to define what is meant by a quantum computer, it's a device that uses, maybe I should define once again the quantum information. Many of you are familiar with information, the word information. It is related to the randomness of a particular event. And so if you have a lot of information, that means there's a lot of randomness or in the system. Many times you think of coin tossing experiments to understand what is information. If you toss a coin, you get head or tail. That means there's some information in that. Unless you reveal whether it is head or tail, there is some information in that. Okay. So there are a lot of other concepts that you must have already studied, like entropy and so on and so forth. There's a large number of information, many bits of information, and so on. So we use bits to understand or to define classical information. That means the states of the object are well defined, head or tail, or 0 volts or 1 volt. That is the classical information. When we talk about quantum information, we said that there are states of the object. For example, you can define 0 bit, or let us call it, people call it qubit, 0 information defined by horizontal polarization, and 1 information defined by vertical polarization. We said these states are not definite. Is it not? There is a probability distribution functions for each of these. So the angle or the polarization state is not well defined, but by the probability distribution function. As we go along, I will elaborate a little bit more. Okay. Similarly, a quantum communication link is the one which transmits qubit informations. Okay. So historically, Feynman is the one who has first observed that you can do computation with qubits. Okay. See, we know in the present digital world, all your computation are with the bits. But if a particular value is not known, value of a polarization or state of an object is not known, how do you compute is an important question. But as you see, what he meant originally was there are a lot of phenomena which are quantum. For example, the light that you see is quantum in nature. So if you go to the equations corresponding to the light, then whatever computing you do can be called as a quantum computing. So quantum computing, his idea was that you can simulate a quantum phenomena by taking the quantum equations. Is it not? That's the crux of the problem in all the computing world. In all your computers, what you do actually is computing some mathematics. See, when someone says, what do you do with a laptop or a computer? You say that you will browse internet, you will do WhatsApp, all those things. But the original meaning or intention of a computer is to do some calculations, like your calculator. Similarly, the core of all this is computing. We do a lot of computations with the quantum computer. Just as an example, the Schrodinger equation, if you solve using some phenomena, you see, I'm not saying about the quantum computer alone, the quantum system, then you are actually solving a quantum problem. If you are trying to solve a quantum Schrodinger equation, that you are trying to solve a quantum, you are trying to simulate or solve a quantum problem. So that is his idea. Okay. I suppose many of you are getting what I'm trying to say. You have to deviate, you have to somewhat come out of your classical mindset if you want to get into quantum. So this is a timeline of quantum information technology. So starting with the Feynman's idea, then you can start about 1984 is the first protocol, communication protocol called the BB84 protocol. Similarly, there is people have developed a lot of models of quantum computers. Then there's what is called, I mean, as we that later on I'll mention quantum entanglement. There you can generate two objects with correlated properties. That is called the entanglement. In the classical world, you may not find that unless you artificially create. Similarly, 94, you have what is called the Shor's algorithm to factorize large numbers. The importance of that is if you are doing some coding, I suppose if someone is doing coding theory, you can not exactly computer coding. If you are trying to do the real world coding, then you have to translate numbers into some other values. So what people do is, if you have a big number, you can encode it using its factors. Its factors define the number. So the reverse process is very difficult. If you are given a big number to factorize, is difficult. If you are given some n numbers, you can multiply and get a bigger number. That is very easy. Forward problem is easy. So that is importance of Shor's algorithm. Similarly, Grover developed a search algorithm. If you want
Hello,
to have
sir.
a large number
Hello,
of numbers,
hello,
yes,
hello, sir. Sorry to interrupt you, sir.
yes,
Sir, please switch on your
yes.
camera, sir. Switch on your camera, sir.
Yeah,
Camera.
just a minute. Because this
Okay.
is full screen, I'm not
Yeah.
seeing myself, so I'll switch on.
But we can see, sir. We can see. You can switch.
Now it is full screen or not?
No, no, sir. You go back, sir. You go back. You go back, sir. You go back.
Just a minute. From this point you want, or
Yeah.
see, just a minute. Let me first switch on my camera, then we'll worry about.
Yeah.
Just a minute. Where is this? Hello?
Yeah, tell me, sir. Tell
Yeah.
me. You are now you make full screen, sir. Full screen, sir.
Yeah, I'll do it. I'll do it. Just a minute.
Okay. ನೀನೇನ್ change ಮಾಡ್ಬೇಡ ಬಿಡು. Earlier you are.
Yeah, because I was seeing full screen, I did not know whether I'm switched on or not.
Sir, now you don't change, sir. You can go. Okay, sir. No. Now
Yeah, let us get going. So this is the timeline of what all has happened. Now let us jump to recent times. In about 2016 or so, which has developed this first quantum communication. I mean, some of you people can browse the see what are the finer details of this. So that's an important development in the whole of quantum technology. Since then, it's almost more than 8 years since that has happened, and many countries and many groups showed a lot of interest in quantum information technology. That's how you are interested right now. There's a lot of competition between big companies like IBM, Google, HP, and so on and so forth. That is the most important reason why we are having so much of quantum hype nowadays. There's a lot of competition between different groups to develop newer quantum computers and so on. But still, as you observe, the application side is not so much. Okay, that's an important observation that you people should do. And a lot of bulk quantum computers are there. Almost every week or every month, some new development is there happening in quantum computers. So let us get back to the basics. Qubits. I mentioned that the classical bits are defined with respect to physical states like voltages. 0 volt means 0 bit. 1 volt means 1 bit, as an example. Similarly, in the quantum world, I said we have to define with respect to the quantum states of the object. Let us take the simple example of a particle at x equal to 0. Suppose if the particle is at x equal to 0, let us say that its state is defined by the qubit state 0. And if the particle is at the position 1, real axis you please imagine, and if it is at 1, we'll define its state as qubit state 1. What is the difference between the earlier one and now? The classical state and quantum state? I said the position of the object is not well defined. So we know only the probability of the position of the object at x equal to 0. That means there is a at x equal to 0.1, 0.2, etc. and minus 0.1, minus 0.2, etc. So the particle can be at any point on the real axis, but with a different probabilities. So there is a probability distribution function associated with the 0 state, centered around 0. The mean of that PDF is 0. Similarly, the mean of the probability distribution function representing one qubit state is centered around 1. So you imagine two probability distribution functions, one at 0, other one centered at 1. And that ket notation, what you are seeing, vertical bar 0 and greater than symbol, is called the ket notation and represents the average of that PDF. Okay, similarly, average of the one qubit state is defined by that ket 1. This is the correspondence. Then the question comes, what is the actual state of the particle? Is it at 0 or 1? So the answer is, it can be anywhere on the real axis, in between or outside or anywhere, which can be represented as a superposition of the 0 state and 1 state.
Sir, you are not audible. Sir, you are not audible.
State or 1. This Bloch sphere. Bloch sphere is the one wherein you take 0 quantum states and quantum information. And there are a lot of techniques nowadays. lot of mathematics has been developed around this to computing and various functions. So I would like to just mention that the same theta, okay, multiplied by the mean of those. So now let us move on to multiple qubits. If you want to talk about 2 qubits, what do you do? We said each qubit state is described by its PDF. So if you have 2 different objects, then you can think of 2 different PDFs and then yes, and a combination of those.
Hello? Hello? Hello?
More
Hello?
joint PDFs. Yes.
Hello, sir. There is some network issue, sir. Now it's okay. Sometimes it is interrupting, sir.
Yes.
From your side, is it
Oh,
okay?
I am seeing everything all right, but network I will not know. I am seeing my slides. So
now
you can ask me when such thing happens for a longer time, then we'll go back a few slides and then get going. Okay.
Sir, go back to a couple of slides back, sir.
See, this is the definition and the operation of qubit.
No,
This
another
timeline.
next timeline is okay. Next slide, sir. Next slide. Next.
Yeah, this
No,
these are multiple qubits.
okay, sir. Multiple qubits, okay.
Yes. So multiple qubits you have to define with respect to joint PDFs. Okay. And then you have for 2 qubit system, you have 4
Sir, again, there is a network issue, sir. Sir, am I audible?
0001 is another qubit state. 0010 is another one, and 1111. So like this, you can translate these into matrix form and then you can operate. It can be directly correlated. If you work out a little bit of linear algebra, it will become very easy to appreciate the transition. You need not work with PDFs. Of course, you can after some time you can forget PDF and work with matrices and various operations. Okay. So now for a 4 qubit or a 2 qubit system, there is no pictorial representation because there are 4 variables here. Okay, so you can imagine, like in mathematics, you can imagine an n vector algebra. Okay, so now let us go to some systems. So the simplest ones you can say can be called as gates. You can have single qubit gates or multiple qubit gates. For poly gates or single qubit gates represented by the matrices like that. You can imagine the 0 and 1 qubit state multiplying these matrices. For example, 0 0 you multiply, or 0 1 and 1 0. If you define as a 2 qubit states, you can multiply and get what is the output state. For example, x is performing the NOT operation. If you give 1 0, you will get 0 1. Similarly, other ones, but of course there are strange outcomes. 0 minus I and I 0, because the coefficients alpha and beta can be imaginary. You can get new quantum states possible because of this complex nature of the coefficients. As an example, a simpler example than the complex output, I am putting you Hadamard gate. So 0 qubit is the input, and a linear combination of 0 ket and 1 ket is the output. It is possible to get a qubit state which is both a combination of 0 and 1. So later on, I'll show you a device which can perform this Hadamard operation. So by using matrices, you can easily work out what is the output state of these poly gates and Hadamard gate. They can also be represented like in digital. And I'm showing you a few gates. C naught gate is represented by that matrix given by that. You can see the first four elements of the matrix and last four elements of the matrix. What it shows, 1 0 0 1. Suppose if you have two inputs to this C naught gate, C and T. C can be called as a control qubit and T can be called as a signal qubit. And the operation T operation C is defined by that matrix here. Suppose C is 0 qubit and T is some arbitrary qubit. What happens? The first four elements of the matrix come into picture and it passes through. Whatever you get at the output is same as T. Whereas if qubit state C is 1 1, then you have to look at 0 1 1 0. That means it's performing a NOT operation. So this whole C naught gate operates that when C is 0 qubit, you're getting the pass-through state, and when C is 1 qubit, then you are getting the NOT operation. Similarly, double C naught, C1, C2 are the two control states, and T is the signal. So 8 possible combinations, C1, C2, and T. So you have 8 by 8 matrix, and you can observe what are the various states. So when C1 and C2 equal to 0, then you have the pass-through state of T, and when C1 and C2 are 1, you have the last part, not state of this. So all the lot of combinations are possible. You can just work out on this matrix. So you can also have people talk about what can be a standard or a universal gate. Like in digital, we use NAND operations, for example. So you can create analogs of classical gates in the quantum also. You have to properly define the matrices. And of course, the most important question you already have, I think, in your mind is how do we create, what circuit will do this? That's a bigger question, and it's a technological problem. It's not so straightforward as in electronics, because these are all quantum systems. We want some strange output like a Hadamard operation. So there is no classical gate which can do such operations. Then when you are trying to talk about quantum information systems, you have a lot of criteria. So what are the various requirements we want to build a quantum information system? These are defined in terms of what are called DiVincenzo criteria. This is the name of a scientist who has announced all these things, who has formulated these things. There is a standard paper is there, which is shown below here. You need to, so the various, a few of them I will highlight. You need to have a scalable physical system with well-characterized qubits. The qubit states to be well defined for that system. For example, a system of photons. And you must be able to scale it. If you have two qubit states, you must be able to extend it to scaling to as easier extent can be thought of as an extension. You must be able to 8 qubit, 16 qubit, or 1000 qubit. You must be able to extend the properties to bigger systems. And there should also be a mechanism to initialize the states of qubits. This is slightly simpler, even though you may not be able to define the output. You can pass through certain systems and say these are the initial states of the qubit of the system. And of course, there is an important property of these states called decoherence. The quantum states of the objects are not so stable as in the conventional information systems. So the states change with the time and with propagation and so on. So you should have to choose the states which are relatively stable. That stability criterion is called the coherence. So, and also like in the digital, we should have a universal set of quantum gates. Do you think the NOT gate is useful, or NAND gate, or any other quantum gate? So we must also have a mechanism to guess or measure the quantum state. You may not be able to measure, because once you measure, the state is disturbed and you cannot get back, and so on. There are a lot of other criteria like that. So let us look at how a typical quantum computer looks like. This is a block diagram which shows, of course, very crudely. And of course, there's some quantum notation is also given here if you look at the paper. So you can start with a mathematical model. See, if you want to be able to do, you have to define what is the problem you'd like to solve. See, create a fully general purpose quantum computer. Even conventional computers, they started with some simple operations like multiplication of numbers, exchange of numbers, sorting of numbers, and so on. We have to break down our program or quantum computer design into small units. What are the various functions we would like to do? If you are studying the microprocessor, so many operations are there with respect to registers and so on, and how you will achieve this and so on. Similarly, you should think about a quantum computer in terms of basic elements. For example, some quantum operations like logic operations or multiplication of numbers and so on. In fact, it is also possible to think of quantum computers in terms of a bigger functions like searching. Suppose you define search operation using so and so operations and so such a unit, then you can make a combination of these to make a bigger quantum computer. People are thinking in that direction, not simply in terms of smaller elemental computers that we are familiar with in digital. Okay, so you have to convert it into computational formulation, then you have to translate into compiler, quantum compiler you can call it, and then you have to build, which can be called as a software for that. And of course, finally, you have to identify a physical system which can implement that. For example, a system of polarizers or optical devices may be able to represent the quantum computer. See, finally, we have to boil down to the hardware sort of thing. So in the design, these are the various stages. You can just click out them. You have a quantum program. The front end is there because human beings, we are understanding in a certain way. Inside the quantum computer, it is happening in a different way. So you should have an interface and translate this quantum program into the technology dependent units. And you have to optimize. A lot of optimization has to be done. And there is what is called, people try to test using a simulator. Suppose you have certain technology, certain units or devices, then you have to see what they are doing. That what is simulation. Okay, so most of the time you operate at an abstract level, like in the case of internet, for example, you have your 7-layer model. Similarly, you must abstract and then later on translate into physical devices. So these are all the various stages. You have the quantum algorithms into a number of circuits, a succession of circuits, and then machine instructions. So when you go to communication, then an important requirement there is you are transmitted from one point to the other. They are not lying at the same position. So what are the issues that come along with the quantum communication? So if you want to build a quantum communication link, you have to define what is the nature of objects that you would like to use, how to represent the quantum information, then the corresponding devices. Like for example, you may have to think of a single photon source, you may have to think of a detector, then you have to study the channel properties. Suppose you want to use a free space between 2 points to communicate, you have to see what is the property. Is there anything new or different compared to classical channel? And then the most important one in communication, the noise. How does it affect? Is the noise also quantum, or is it only traditional type? And also many of nowadays a lot of security issues. That means that someone is trying to disturb or steal the information. All these aspects we have to consider. Okay, there are a lot of physical things that people are talking about. Spin of an electron or angular momentum of a photon. These are all the various quantum properties that people try to use for quantum communication. So a lot of developments are taking place in that direction. So one slide I would like to put about the entanglement, which is a very useful property in quantum communication. You have correlated properties, or what you can call as, that's a good word to use, correlation. So if you toss 2 coins, generally independently, you don't know what is the outcome of each separately. But if they are correlated, if you know the property of one experiment, you can predict the outcome of the other experiment. For example, if the first one is head, second one also can be head. So then you can say these are correlated or entangled. You can generate objects which are entangled. In quantum world, you photons which have got correlated properties. Okay, you can imagine that these coins to be tied by some small string, so that if one goes head, the other also goes head. So now what you have to do is you have to work out all the quantum states possible for an entangled system. So I have represented by phi plus and phi minus, psi plus and psi minus. These are just as an example. So this can be, these are all a subset of the all possible quantum states of a 2-qubit system. So you can say these are the 4 qubit states you can make use, and they are correlated. So they can be used to perform many quantum information functions. So let us look at one example of a cryptographic system, how you can say that quantum is a very secure cryptographic system. So in the quantum world, people use Alice and Bob as the transmitter and receiver, and there is a dedicated quantum channel for exchanging the quantum information like the header information, etc. But the actual data, because the enormity of data, a public channel, in this example, a public channel is used. Okay, and Eve is trying to steal the information, try to disturb the, she is connected to the quantum channel, is trying to disturb what is happening. So we'll have to work out what happens when there's a 1 qubit Alice wants to send, and means you are using not only 1 qubit state and 0 qubit state, but there are many qubit states, like 4 qubit states, D1, D2, D3, D4. You know very well now that the psi, the value of the wave function, can take any values. You can easily pick up 4 qubit states and then work out all the quantum information theory with respect to 4 qubit states. And also people talk about what is called the device independent properties. All the theorems or many of the announcements will be made in terms of device independent, whether you use electronic system or photonic system or any other system, they will remain valid. That's what is meant by device independent properties. Let us take the example, then we'll discuss. So this is just for illustration. In physically, people may not do like this. You may do on the chip or on an optical table. So bulb is representing the source of quantum information. And this side, this below, before this dotted line, is the Alice area. Alice has got 2 mechanisms to represent quantum information. First one is called the horizontal and vertical. In this, you have two polarizers. If you pass through the first one, it is a horizontally polarized qubit state output. And the second, and when you there's a vertical polarization for the 1 qubit state. 0 qubit state is represented by horizontal polarization, 1 qubit state by vertical polarization. Similarly, an alternative basis is possible. See, when you're talking about this alpha into 0 ket plus beta into 1 ket, that 0 state and 1 state are defined in a particular way. In this example, I said just now that 0 state is represented by horizontal polarization, 1 state by the vertical polarization. Similarly, it is also possible to represent by an alternative basis, minus 45 degrees for 0 state and plus 45 degrees, 1 state. This is an alternative way. Both, there can be equivalence. You can also convert between the 2 different bases. Okay, but in this protocol, let us agree that Alice has 2 different possibilities. Okay, and how does Alice decide whether to choose the first basis or second basis? Is the important question here in BB84. What the protocol here is, Alice will choose these basis states randomly. Let us assume randomly Alice will choose the first one, and you can also think of it as 2 black boxes or 2 machines. If you pass through the first one, you get a 0 qubit state or 1 qubit state. If you pass through the second box, you will get minus 45 or plus 45. So let us work out now. There's a qubit 1. This is a bit sequence that I'm trying to work out. 1 1 0 0 0 1 0 0 1 0 1 0. So if you pass this qubit state through this first polarizers, then you get corresponding. One means you get vertical polarization. Then 1 means vertical polarization. 0 means horizontal polarization, etc. If Alice uses only the first machine or the first box, if Alice uses second box, you know what comes out. But here in this protocol, Alice will choose randomly these two. Let me say she can toss a coin and then decide which. So, and corresponding outcomes is what I have listed here. 1 through minus 45, 40 plus 45 basis. Next one through horizontal vertical basis. Next through horizontal vertical basis, and so on. So these are all the photon sequences, polarization states corresponding to this bit sequence. And then they're transmitted. Now at the bob end, how does she do? She has to do exactly what Alice has done. If Alice chooses horizontal polarization, Bob also has to choose what horizontal polarization. If Alice chooses minus 45 plus 45, Bob also has to choose plus 45 minus 45. But then there is no security associated with that. Is it not? So Alice in this protocol, Bob also chooses randomly the polarization. So what you have to do, you have to work out all the possibilities of Alice sending 0 qubit through first machine, Bob receiving 0 qubit through first machine, Alice sending 1 qubit through second machine, Bob receiving through first machine. All combinations you have to work out and see whether they are receiving correctly or not. So this is what is given here. The second, this line, this plus minus square boxes represent basis sequence for Bob and the corresponding outcome. If he uses plus or horizontal vertical, Bob will get 0 qubit, which is not correct. Okay, this combination is not correct. Similarly, what 1 qubit state represented by horizontal vertical and represented by once again the horizontal vertical is a correct representation. It is not exactly same. See, it's not exactly same as this. There are cross. If you would like to, you check up one of them. For example, you take the example of a say horizontal vertical somewhere representing. So what happens? You see the outcomes are like this. Out of all these possibilities, 16 possibilities, only 8 are correct. That means the lookup table that these people have to use for exchanging quantum information consists of only these 8 possibilities. Okay, so you have to. So this is the crux of the protocol. So that's how they. So Alice will send a qubit state using some basis vector. Bob also randomly picks up his qubit state using a basis, and then they will check up from the lookup table whether you have got a 0 qubit or 1 qubit. So how do you think this protocol will bring in security? So you imagine an Eve trying to disturb the system. What she does is she knows that these two people are using the BB84 protocol. So she will get 4 machines, 2 horizontal vertical.
Sir, you are not audible.
Eve to Bob, another 50%. That means only 25% of the elements are correct. The lookup table consists of only 25% out, which indicates that there is a disturbance in the system or someone is trying to manipulate. Okay, that's how this V84 protocol works. There are a lot of variations of this, and I hope some of you will go back and work out all the possibilities carefully and what happens if something else is chosen, and so on and so forth. I hope I have illustrated this BB84 protocol, and if you work out, you'll be able to understand further. Okay, so let me get back to some standard developments. This is the picture of Amisha's 1 satellite from the Chinese Academy, and a lot of new developments are there now. And many other countries also have satellite-based communication. India is also trying to get it. We have projects where there can be satellite communication between the different points, even from ground to the satellite, satellite to satellite, etc. So more and more will happen in the near future. But of course, still we are slightly lagging behind, you can say. Of course, overall itself, the quantum technology is developing and people are waiting for a breakthroughs, which can change many things. Okay, please try to look for such breakthroughs. I hope many of you are interested in using developing certain systems, algorithms to solve some problems. But please keep in mind
Sir, you are now.
broadcast. It's not exactly same as the broadcast network. Okay, I think I'm slightly far away from the mic. I hope you are able to hear now. So there's a lot of activity going on the research going on the quantum internet. Let me get back to a little bit of photonics. So photonics can be considered, as I mentioned earlier, photonics is a good technology to represent quantum systems. So photonics can be considered as a science technology involving light wave particles. You can say it is analogous to electronics, and you have to look at the fundamental properties of photon, like bosonic nature, to exploit it for the quantum applications. Then all the conventional operations that we have been doing, generation, transmission, control, processing, and display of light, can be done using photons. Maybe storage is a difficult thing right now, and a lot of quantum properties also you have seen that we can use light wave particles to represent. Then a lot of things to come in the real world. If you see, photonics has got a lot of applications, starting from the optical communication to industrial applications, biomedical sensors, and now the quantum, and so on and so forth. So many countries have developed their programs, photonics programs, and also quantum, of course. So a lot of academic activity is also going on. Many universities are doing research in this photonics. If someone wants to do research after this, your BTech or MTech, it's a very good subject. Of course, I'm not assuring what jobs you'll get and all that. That's a different discussion altogether. Then there are a lot of national initiatives. Many countries have got their own national programs. Indian government also has allotted a lot of money for the research on photonics and quantum. So let me show you a few slides how photonics can be used in the quantum. So this is a picture which shows integrated technology. See, everything we said in the beginning that we have to imitate VLSI. So all the devices we have to do integrated photonics. That means they are based on the optical waveguides and couplers, and then controlled by electrodes, and so on and so forth. So this is different from what can be called as bulk photonics, bulk optics. So opposite of integrated photonics is the bulk optics. So where you develop small prisms, mirrors, and so on. Here you work with optical waveguides, couplers, and all that. As you know, silicon is the dominant technology for this photonics. And in the future, people foresee that 3.5 technology is more important, because you cannot make lasers and active components on silicon. And as an intermediate phase, people use nonlinear properties of the crystals like lithium, battery, and not glass. Some crystals which have got nonlinear properties to represent photonic quantum technology. And also a lot of things are coming up in the near future. So let me show you a few more pictures on the devices. So this is a picture which shows generation and manipulation of qubits using photonic circuits. So these are just examples. You can see that paper for this. You can observe that there are the components. If you are already learning a little bit of photonics, you can see that there are ring resonators, Bragg reflectors, and so on to do such manipulation. So one or two more slides I'll show you, and then go to our work. So this is also about generation and manipulation of photons. I'm giving you the references below. You can please have a look at them. Then one more slide. This is how a full picture looks like. Integrated quantum communication device, they call. So a lot of technologies are there, like nitrates and so on, people use. So people have also developed entire QKD on a chip. They have proposed, I mean, it's not a real fabricated or practical device, but if you have to make a QKD system, you can make it like this. These are all the lot of electronics you can also find. Then let me go back. I think we are running short of time. So I'll show a little bit of work that we have been doing in our lab before we conclude. So these are the topics that we have worked on. We have worked on quantum algorithms. Then how to, you see, one of the emphasis that we are trying to put is on how to implement using photonic devices. So one of the recent works is on higher dimensional QKD. You use qubits instead of qubits. And then another problem that we are trying to tackle is to use the modes of optical waveguides to represent quantum information. Instead of representing by horizontal and vertical polarization, you can use mode 1 or TE mode for horizontal, TE mode for 0 qubit state and TM mode for 1 qubit state. And also Mr. Rohit, his paper is quoted here. He has worked out a higher dimensional version of this BB84 protocol you just now talked about. Then we have also worked out angular momentum properties, which is nowadays very hot subject in quantum photonics. So just as an example, I'm showing you one example where you have a Y branch. The middle picture is showing you Y branch. In the input, there are two modes, TE0 mode and TE1 mode. You know the pictures of mode patterns, is it not? 0 qubit state is represented by T0 state, and T1 state represents the 1 qubit state. And a Y branch typically conventionally divides the power. It can divide the power between two output ports. It can also divide the mode. Mode splitting also it can do. But if you work out the Y branch state, you observe that output is a linear combination of 0 ket and 1 ket. And 0 ket minus 1 ket. That means the typical Y branch is following, is creating a Hadamard gate. So this is a practical implementation. We use photonic bandgap structures to fabricate these gates. So this is the implementation of BB84 in higher dimensions. And then this work from another of our colleagues in our department. They are working on photon sources, generating single photon sources, etc. They use nonlinear properties of this ring resonator. You have a nonlinear layer, cladding layer, and they can create entangled photon sources, single photon sources, and so on. So please come. So I think we can conclude. This is a pictures from some of our IEEE programs. We have a lot of visitors coming and a lot of activity going on. So thank you very much for listening. I hope you have a lot of questions. And of course, Srikanth and others also will be able to answer many of the questions that you have. And I'm very happy that you have done this International Light Day program. Okay, please keep doing. And also please help other colleges near in the Malad region to set up photonics chapters and take up photonics activities. I hope many of you are already members in this, and thank you very much for listening. If you have questions, I'll take.
Hello.
So
thank you very much, sir.
These are some of the theses from our old students.
Now,
Kalwal
1
Rai
minute,
worked on algorithmic engineering, and all these papers are there here. These slides are there with. I can give you once again if you want, so you can look at some of these papers. Then Akshta has worked on information processing. I mean, like random number generation and so on, cryptography, etc. Then Bhavani, he has combined machine learning with quantum functions, etc. That's all. Thank you.
So thank you, sir. Any questions
Yes.
from students? Any questions regarding quantum? Then, if you don't have a question, I will only ask question for sir.
Yes.
Okay. Sir, actually, how many qubits you can go? You have shown die bit, tri bit like that, sir. Now, right now, how many qubits they are operating, sir?
See, there are a lot of, I mean, they are changing rapidly. You
Ah.
have multi-qubit systems. See, in our lab, we have worked on 8 qubits and 16 qubits.
16
Levels.
up to you.
I mean, you are talking about levels, not exactly qubit state systems. You see, I suppose you are talking about higher dimensional QKD. Is it not?
Oh,
Higher
yes, sir.
dimensional QKD means instead of having only 0 qubit state and 1 qubit state, you have intermediate states. You can have 4 and 8 and easily. Then what happens is all the disturbances will be there, like decoherence and all will not allow you to operate. A lot of, like in multi-channel communication, you will have a lot of cross-channel problems. That's why you cannot
Okay.
go higher. But hopefully in the future, people can work out with a lot of what is called orthogonal states. So you can go much
Yeah.
higher.
So when you go for orthogonal state, then bandwidth will be doubled.
Not exactly double. I forgot to mention that is an exponential. See, when you go to multi-qubit states, it's a 2 qubit state will give you 4 basis states. Similarly, 3 state will give you 8 basis states. So it is going exponentially, very large volume of computation that is possible with few qubits. That means if you have a 64 bit computer, it is equivalent to only a 5 qubit quantum computer, something like that. Of course, a very crude way to assess. You have to go more theoretically if you want to estimate the quantum entropy and all those things.
So, okay, sir.
Yes.
Thank you, sir. Sir, one more thing on behalf of my students. If some of them are interested, I'll bring them to your lab, sir, so that you can explain. You can explain.
Yeah,
what,
just for observing, you can come. But next 2 months, I'm not in Bangalore.
Where are
Our
you going,
students
sir?
are there. Our students are there, and you can also discuss.
No, sir.
No, I'm in Hyderabad right now.
Okay, you're in IIT
See,
Hyderabad,
it's like
no,
a
sir?
vacation. I have never taken a vacation from IISC.
Okay.
Not IIT. This is called CB8, Chaitanya Bharat Institute.
Okay. After 2 months, we'll meet, sir. After 2 months, we'll meet, sir.
No, in between I'm there. Once in a while I'm there, but your students are welcome. Our students are there. A couple of students are working on quantum. Mr. Viresh, one student, is working on quantum error correction.
Yeah.
That is his subject. And he's also trying to implement quantum error correction using FPGAs and all that hardware, along with Dr. Shulila. We are working on the quantum error.
Okay. Sir, actually, during your availability only, we'll book some appointments, sir. I'll bring my students, sir, those who are interested. When you come to IIC, sir. Hello? 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 Shall we leave? Hello? Record off ಮಾಡ್ಬಿಡ್ತೀನಿ recording. Hello? Hello?